Let's continue with agglomerative hierarchical clustering. In this example number 2, we will see some data about customers. As you can see here in this table, customer ID, gender, age, annual income, spending score. This spending score, of course, is related to some data here, as we will see how we can create some clusters around this information if the cluster is depending on age or annual income, or just they are grouping based in the spending score. Okay, for this we will not need a customer ID. The gender, we're gonna make this a little bit difficult. Could be that all the information could be related to female, so we're gonna delete this variable, this feature. Okay, remember one step here, if we wanted to use gender, is to convert male and female to a quantitative variable. In this case, this is a category variable, a nominal variable, and we should change it to 1 and zeros. For example, 1 for male, 0 for female, right? Okay. Once we have done this, as we can see here, we have 200 observations and 5 columns. However, as I'm saying, the next step is to eliminate or delete one column. We're gonna drop it. We're not gonna drop customer ID and gender, so you can see, as we saw in the last example, we drop the columns. Axis 1 to tell Python that this is based in columns. Okay, this is another way to do it too. If you want to improve your Python skills, there could be another one using ilog and then values. So we say then columns. Okay, and as you can see, we have reduced our shape or dimensions. Now it's 200 observation and 3 columns. Okay, what is next step? As you remember, we have discussed this about hierarchical clustering or density-based clustering or k-means or other clustering method, is to normalize data. Some algorithms are more susceptible and some others not, but the best way is to normalize data. This is even help us when we plot the information. You will see how this plot looks better, okay, and different. It's gonna be more clear. It's gonna be clearer to see. Okay. Okay, now how to normalize, following the procedures we saw in the last example. We use the function normalize. We normalize the whole data, but when we normalize, it is not exactly a data frame, so we have to convert it using the pandas. And we say, we call, as you can see here, we have to pass the names of the columns. It's important. And once we have done this, we can see that all the variables values are between 0 and 1. Okay, age, annual income, and spending score, all these variables are in the range of 0 and 1. Now, the next step when we are working with some hierarchical clustering is to visualize the dendrogram. The same method we used in the previous example, we use it here, is the method warn, trying to reduce the variance. We create the linkage between all the data. Remember, is calculate the distance between each point, and that's how the dendrogram is created. Then, as you can see here, for this customer information, it depends the cut we want to, or the number of clusters we prefer, and that's how the dendrogram will be cut. Here we have a small group of data together, another one, 1, 2, 3, 4, if we consider it like this, 4, 5, 6, 7. Could be 7 clusters if I am around less than 1. Okay, that distance less than 1. Okay, but what if I use 2? It's gonna have 1, 2, 3, 4, and 5. We are gonna have 5 clusters. So that's one of the disadvantages of using hierarchical clustering, is not to have exactly the algorithm, or we don't let the algorithm to decide how many clusters is the better choice. Okay. So where to cut it? That's the problem. Okay, where we cut it? If we cut around 2, as I said, we create a horizontal line around y equals 2. As we can see, we cut the difference of observation based on the distance among them. Remember to use the function shc we call linkage. All this was seen in the previous example. Okay, we call pandas, numpy, matplotlib. Normalize is in the scikit-learn. Okay. Also, you need a function hierarchical from scipy. Okay, we call it shc. Okay, so we need scikit-learn, scipy to create all this. Okay, let's move on. Once we have decided how many clusters we would prefer, for example, 1, 2, and 3. For example, the green one, the orange one, and the red one. That means that we cut our dendrogram around 2.2, the distance among the observations. What we obtain? What we got? I said, okay, agglomerative clustering. I want 3 clusters with the Euclidean distance and the linkage worked, as we saw previously to build our dendrogram. Okay, so we have to be consistent in what we're showing, or working in the dendrogram and working with the agglomerative clustering. Okay, it's important. Okay, once we have done this, we can see that Python output is 0, 1, and 2. We have 3 different clusterings, and we will see when we plot the results how the different variables are related. Okay, so the first observation belongs to the first cluster, the second one too, but the third observation is for the second cluster. Okay, let's see a little bit what is the difference between among these ones. For example, here the age is not different, it's not too distant. 19 and 21, they are very close, and 20. So that means that age is not a variable that is gonna separate or partitionate our data. The annual income too, it's really close. The values are really close. However, spending a score is a variable with a long distance among our observations. Here 81 and 39. Of course, 6 is closer to 39 than 39 is closer to 81, but the age and annual income could be variables that tend or impact in the where these 2 or 3 observations will belong, to the first cluster or second cluster. Okay, here spending a score was a strong variable, or has a huge impact to where our observations belong to in any clusters. Okay, the 77 could be close to, we see, to the second observation. Let's see if the, well, in this case is the fourth observation, belongs to the first cluster, or okay, or what is the result. Okay, here it is. As you can see, not only spending a score it's important for clustering, also the other variables have a maybe a smaller impact in our clusters, or how to cluster our data. So it's important to we have used the other variables too. And let's see the results. Let's see the results when we plot this. Okay, so you can see these variables here is this one is age and annual income. I'm not plotting spending score. However, look at this here, what we got. You can go and try. You can try out using spending score too, of course, just changing here. And let's see that even using these two variables, age and annual income, we can partitionate our data in 3 different clusters. Perfect differentiate clusters. Here, it is a little bit complicated to understand this variable, age and annual income, because they are normalized. However, look at these groups, how this cloud of points are perfectly, or it is perfectly clear to identify the 3 different clusters. Okay, but what happens if I don't normalize the data? Here it is. Okay, we also can clearly see the 3 different clusters. There is a bit of just a position here between these points. However, we can identify this cloud around here between 40 years, I mean 40 years and 60 years, and 80 to 140,000 for the annual income, to be the majority of for the cluster 3. Okay, when a person is between 40 or 60 years old and also has an annual income of $80,000 to $140,000, will belong to the cluster, well, to the red cluster. The same we can say about the green cluster, where what is the majority of people that belong to the green cluster? Okay, it's people around 30 to 70 years old, also with less than $80,000 as annual income. Okay, that means that hierarchical clustering in this case, in these 3 variables, can allow us to identify how are the attributes or features for each person, to label them as part of one cluster or other one. Okay, there are different labels. Okay, now let's see the definitive proof about hierarchical clustering using some synthetic data. I'm gonna use this data from the HDB scan creators. You can access to this data, or you can download it with this link. Okay, it's a 2-dimensional data only, however with 2,309 observations. Okay, so we are perfectly fine to plot it in a Cartesian plane as follow. Look at this here. We have, how many clusters can you see here? I can tell you that I see 6 clusters. 1, 2, 3, 4, 5, 6. And also I can see some noisy points. Okay, there's noise data here around. So we're going to ask, or going to prove, if the agglomerative hierarchical clustering is capable of identifying these clouds. Of course, perfectly partitionate the data. Okay, that means it has to perfectly identify 1, 2, 3, 4, 5, 6 cloud of points. And let's talk about the noisy points too. It's a agglomerative clustering capable of create or to label data as noise. Let's see. Okay, our data will call data. Okay. Okay, as usual, let's see the customer dendrograms. Well, sorry, in this case it's not customer data. Customer dendrogram is how can call it clusterable data. Okay, there's a small mistake there in the title only. Okay, the same SHC dendrogram, we call the function dendrogram from scipy, the linkage 2 using the usual method word. As you can see, we have 3 different colors, well actually 4, but it depends on us where to cut our dendrogram, how many clusters. Okay, we already know that there are 6 clusters, or that's what I think, or that's what I believe. Okay, there are 6 different clusters. So let's see where the cluster, or these 6 clusters can be found, where I have to cut the dendrogram to see 6 different, using a distance of 4, 6. Let's move around 6. We can see if we cut the dendrogram here is 1, 2, 3, and 4. That means that the cluster ones we call clusters, or calling clusters, it would be only 4 clusters. Let's see around here in 5, 1, 2, 3, 4, 5. That means that the dendrogram only identified 4 or 5 clusters. However, let's move a little bit down below here in 4. Is 1, 2, 3, 4, 5, 6. Okay, it is capable of identifying 6 clusters. Okay, that means that when we call the function agglomerative clustering, the dendrogram will be cut in 6 different parts. Okay, let's see. But if it's gonna cut it in 6 different parts, that means that there are not gonna be noisy points. Okay, it's important to understand this part. Let's see next. Okay. Well, this is around the line 4, as I was saying. Well, let's move on a little bit more. Okay, we call the function agglomerative clustering with 6 clusters, and that's the usual linkage, the usual distance, the Euclidean. Okay, and here the result. Okay, you see the different labels here. The first point belongs to the second cluster, and so on. Okay, and let's see the result. What is next? Okay, you see, is 1, 2, 3, 4, 5, 6 clusters. There are 6 clusters. Oh yes, identify 6 clusters. Of course, it identified 6 clusters because I told Python, or I told the function agglomerative clustering to identify 6 clusters. But I already know what the results have to be. Okay, yeah. What? Okay, 6 different clouds and some noisy points. 1 cloud here. Okay, 1. A second cloud here. However, here, as you can see here, this part here, okay, this red cloud should be 1 together with the other orange point here. That means that there is an error here for the agglomerative cluster. Okay, this one, okay, perfectly identified this cloud perfectly. Okay, well, they have 2 for 3, 2 out of 3. This one, okay, perfect. The red one, yes, identifies this cloud. Okay, that means that 3 out of 4. Oh, what's going on here? There must be 2 clusters. Yes, there are 2 clusters, purple and green one. However, this line of points, and the other one here, it looks like a squid. Okay, here there is a mistake right here. Okay, and well, actually in the 2 clusters. Okay, this cluster should be 1, and this cluster should be only 1. Okay, that means that hierarchical clustering has had 3 errors here, or 3 mistakes. Okay, when clustering the data. Okay, that means that these cloudy points were wrongly labeled. Okay, however, as you can see, that doesn't mean that hierarchical clustering is a bad clustering. No, there's just some data is more suitable or better to fit with hierarchical clustering than other data points. Okay, so we will see in next videos what is the best clustering algorithm for this kind of data points. Okay. Well, I hope you like this. Thumbs up and see you soon.